Hi, this is Stu Schwartz from MasterMathMentor.com. This is video BC07a. The topic is work, and it covers the BC manual pages 157 through 161. Work is done when moving an object from one place to another. Work is done when lifting an object, moving a car from one location to another, towing a water skier, or perhaps lifting a payload into space. When we do work problems, we are concerned with several types of situations. The first and simplest is when the force applied to the object is constant. If an object is moved a distance d in the direction of an applied constant force F, then the work done W is defined as W equals F times D. Force can be thought of as a push or a pull, one that changes the state of rest or motion of an object. If the gravitational forces are on Earth, then force is usually measured as the weight of an object. So if James lifts a 30-pound box 3 feet, as shown in the picture, we'd like to find out how much work is done. And the answer is simple. Work is equal to force times distance, which is 30 times 3, and we get 90, and the measurement is foot-pounds. In countries that do not normally use the metric system, like the United States, work is usually measured in foot-pounds, inch-pounds, foot-tons, or perhaps even mile-tons. If the force involved in moving an object is constant, work is easy to calculate. But typically the force is not constant. For example, it takes more force to get a bicycle moving than to keep it moving. It's easier to compress a spring the first inch than the second inch. Suppose we have a leaky bucket that we are hauling up from the bottom of a well. We will say that this bucket has a weight, which we know is a force, and we will denote it by F1. We now move our bucket up a distance of delta x sub 1. So the work to move the bucket is W sub 1 is equal to F sub 1 delta x sub 1. The bucket has lost water, so it now weighs F sub 2. We now move our bucket up a distance of delta x sub 2. So the work to move the bucket is W sub 2 equals F sub 2 delta x sub 2. The bucket has now lost more water, so now it weighs F3. So we move our bucket up a distance of delta x3. So the work to move the bucket is W sub 3 equals F sub 3 delta x sub 3. And now the bucket has lost more water, so it now weighs F sub 4. So we move our bucket up a distance of delta x sub 4, and the work to move the bucket is W sub 4 equals F sub 4 delta x sub 4. It should be clear what is going on here. The total amount of work to move the bucket to the top of the well is W equals summation I equals 1 to infinity of F sub I delta x sub I. However, realize that the water is leaking from the bucket at a continuous rate. So we need to make our delta x sub i's as small as possible. So W is equal to the limit as delta x sub I approaches 0 of the summation I equals 1 to infinity of F sub I delta x sub I. We know that this formula represents a definite integral. So we define the amount of work done when an object is moved along a straight line from x is equal to a to x is equal to b by a continuously varying force f of x as w is equal to the integral from a to b of f of x dx. There are two types of work problems that are common. It is helpful that we classify our work problems because each of them has a slightly different formula. The most common type involves moving an entire object a small part of the distance. In this case, the dx part of the integral represents the small distance that the entire object must be moved. So the formula for the change in work is the force times the distance increment, which is f of x delta x. And therefore our formula for work is equal to the integral from position A to position B of f of x dx. Examples of this are compressing a spring, propelling a satellite into space, raising a ship's anchor, gas expanding, or pushing an object across the ground. We will see examples of each. Our first example in work done by moving an entire object part of the distance is stretching or compressing a spring. This is governed by Hooke's law that states that the force F required to compress or stretch a spring is proportional to the distance x that the spring is compressed or stretched. If k is small, then not a lot of force is required to stretch the spring, while if k is large, then it's quite difficult to stretch or compress the spring. We say, therefore, that F is equal to kx. In problem 1, we are told that a force of 50 pounds compresses a 20-inch spring 5 inches from its natural state. And we are interested in problems where we want to find how much work is done in compressing the spring different distances. We see by the picture the situation. When x is 20 inches, our spring is in its natural state, and therefore F is equal to 0. There's no force on it. However, when we compress it 5 inches, that takes x down to 15, and the force is 50. Any question involving work requires us to find our constant of proportionality k. We know that F is equal to kx, and when F is equal to 50, x is equal to 5. So 50 is equal to 5k, making k equal to 10. We first want to determine how much work is required to compress our spring 5 inches. And then we would like to find how much work is required to compress our spring an additional 5 inches. Our formula for work will be a definite integral from compression position 1 to compression position 2 of force times distance. Our compression position 1 is 0, and our compression position 2 is 5. Our force is 10x, and our distance is dx. So we want to integrate from 0 to 5 of 10x dx, which is 5x squared evaluated from 0 to 5, and our answer is 125 inch-pounds. If we want to compress our spring an additional 5 inches, our integrand remains the same, but now we integrate from 5 to 10. We end up getting 5x squared evaluated from 5 to 10, and we get 375 inch-pounds. So 3 times as much work is done compressing the spring an additional 5 inches as opposed to the first 5 inches. Number 2 reads, you push a chair on casters across the floor with a force F equals 20x E raised to the negative 2x over 5, where F is the force in pounds and x is the distance in feet you push the chair. This, too, is an example of moving the entire object, in this case the chair, little distances at a time, with variable forces. As shown by the graph of F, it takes considerable force, F, to get the chair moving the first couple of feet. But once it is rolling, less and less force is required to keep it rolling. You are first asked to draw a narrow vertical strip of width dx equals 0.2, centered at x is equal to 4 feet. And then we want to find the force in moving the chair at x is equal to 4, and the amount of work done at x is equal to 4. The force at x is equal to 4 is simply f of 4, which is 20 times 4 times e raised to the negative 8/5 power, which is 162.152 pounds. But the amount of work has to be approximated. When x is equal to 4, our rectangle has an area of 16.152 times 0.02, which is 3.230 foot-pounds. But the shape is not a rectangle. It is closer to a trapezoid. But since our dx is small, the approximation of 3.230 foot-pounds will be close to the definite integral used for area. We now want to find the work to move the chair the first 8 feet. So we set up our integral as work is equal to 20, the integral from 0 to 8, of our f of x, which is x e to the negative 2x over 5, dx. We will do this by integration by parts, where our u is x and our dv is e to the negative 2x over 5 dx. That makes du equal to dx and makes v equal to negative 5/2 e to the negative 2x over 5. So our work becomes 20 times the quantity, negative 5/2, x e to the negative 2x over 5, minus the integral of negative 5/2 e to the negative 2x over 5 dx. That gives 20 times the expression negative 5/2 x e to the negative 2x divided by 5 minus 25 force e to the negative 2x divided by 5, evaluated from 0 to 8. And when the calculation is done, we get 103.6 foot-pounds. So our work is simply 20 integral from 0 to infinity of x e to the negative 2x over 5 dx, which is equal to 20 times negative 5/2 x e to the negative 2x over 5 minus 25 fourths e to the negative 2x over 5, evaluated from 0 to infinity, and that gives the expression negative 50x over e to the 2x over 5 minus 125 over e to the 2x over 5, evaluated from 0 to infinity. We can use L'Hopital's rule for the infinity problems, and we get the limit as x approaches infinity of negative 50 over negative 2/5 e to the 2x over 5 minus 0. And then plugging in 0, we get minus quantity 0 minus 125. Again, using L'Hopital's rule, we get 0 minus negative 125, getting an answer of 125 foot-pounds. So approximately 104 foot-pounds of work were done to move the chair 8 feet. But moving it out from 8 to infinity was only approximately 21 more foot-pounds of work. That's because the force is getting smaller and smaller to move the chair, and the limit of this force approaches 0 as x approaches infinity. Number 3 is another example of moving an entire object a series of small distances. It reads, the weight of a body varies inversely as the square of the distance x from the center of the Earth. So the force f of x exerted by gravity is f of x equals c over x squared. We have a space satellite weighing 1,000 pounds on the surface of the Earth. Assuming that the radius of the Earth is 4,000 miles, how much work is done to propel the satellite into orbit at an altitude of 12,000 miles? In order to use our integration work formula, we first need to find f of x, which means we need to find c. We know that f of x equals c over x squared. And when x is 4,000, which is the surface of the Earth, 4,000 miles from the center, our object weighs 1,000 pounds. So 1,000 equals c over 4,000 squared, and therefore c is equal to 16 billion, or 1.6 times 10 to the 10th power. So if we are interested in lifting just the satellite into an orbit 12,000 miles above the Earth, we integrate 1.6 times 10 to the 10th over x squared dx from the surface of the Earth, 4,000, to 16,000. 16,000 is 12,000 above 4,000. And when we do that, we get negative 1.6 times 10 to the 10th over x, evaluated from 4,000 to 16,000, and we get an answer of 3 million mile-pounds. If we now want to raise the satellite to a height of 60,000 miles, we integrate from 16,000 to 64,000, and we get 750,000 mile-pounds. So if we are interested in what percentage of the work in raising the satellite into orbit is getting it from 12,000 miles to 60,000 miles, we calculate 750,000 over 3,750,000, and we get 20%. So most of the work in getting a satellite into orbit goes into having it leave the Earth's atmosphere. We see that as we get further and further from the surface of the Earth, the work required to lift the satellite to that height gets smaller and smaller. So if we want the total work to get the satellite infinitely high, we look at the work to be the integral from 4,000 to h of 1.6 times 10 to the 10th over x squared dx, which is negative 1.6 times 10 to the 10th over x, evaluated from 4,000 to h. We look at this expression as h approaches infinity, and we end up getting 0 plus 1.6 times 10 to the 10th over 4,000, getting 4 million mile-pounds. In physics, we have an important relationship called Boyles Law. It states that the pressure of a quantity of gas is inversely proportional to its volume, or P is equal to some constant K over V, or PV is equal to a constant. Boyles' law is important. We breathe because of Boyles' law. Balloons work because of Boyles' law. A car combustion engine works when the sudden increase in pressure from the combustion of the fuel expands the cylinder and pushes on the piston, causing the crankshaft to turn. The crankshaft moves a certain distance because of the expansion of the gas, and thus work is created. The picture on the right describes what Boyle's law is saying. We have a gas that is heated to 300 degrees. As shown by the gauges, its pressure is 1 and its volume is 4. There is a cover at the top of the gas attached to a rod. While keeping the temperature the same, we double the pressure, and because of Boyle's law, we have the volume. So the rod now moves down vertically, and since it moves down with some force, work is done by the gas. We can use our integral formula to measure that work. In number 4, we are told that a quantity of gas with initial volume of 2 cubic feet and a pressure of 400 pounds per square foot expands to a volume of 4 cubic feet. We would like to find the work done by the gas. 2 steps here. First, we have to find our constant K, and from there, we can write our formula to find the amount of work done, W. To find K, we use the formula P is equal to K over V, or 400 is equal to K over 2, and we get K to be 800. To find the work done by the gas to change the volume from 2 cubic feet to 4 cubic feet, we let W equal the integral from 2 to 4 of 800 over V. This becomes 800 natural log of V evaluated from 2 to 4, or 800 natural log of 4 minus natural log of 2. We can write natural log of 4 minus natural log of 2 as natural log of 4 over 2, which is the natural log of 2. So our answer is 800 natural log of 2, or 554.518 foot-pounds. Another classic problem in moving an object a little distance at a time is the problem of raising an anchor. We have a ship anchored in 100 feet of water. The anchor weighs 4,500 pounds, and the chain weighs 25 pounds per foot. When the ship gets going, the anchor needs to be pulled into the ship, and we want to know how much work is required to bring the anchor and chain onto the ship. The best way to attack a problem like this is to translate our picture onto a Cartesian plane. And we can do this in one of 2 ways. First, we can place the origin, the point 0, 0, at the bottom of the ocean, and thus the water level will be at the point 0, 100. The anchor will be at the general point 0y during the time that the anchor is raised. So to find out how much chain there is between the water level and the anchor, we subtract top minus bottom, and we get 100 minus y. We can see all those important values in blue. Or we can place the origin, the point 0, 0, at water level. And therefore, the point 0, negative 100 will represent the bottom of the ocean. The anchor is still at the general point 0y. So to find out how much chain there is between the water level and the anchor, we still subtract top minus bottom, or 0 minus y, which is negative y. We see those important values in red. Regardless of how we set it up, we would like to determine how much work is done in bringing the anchor, not the chain, up from the bottom of the ocean. and also the amount of work needed to bring the anchor up from 75 feet from the bottom. This is not a calculus problem because we are moving the entire anchor, which always weighs 4,500 pounds, a finite distance. So we use our formula, work is equal to force times distance, and to bring it up from the bottom, we have 4,500 times 100, or 450,000 foot-pounds. If we want to bring the anchor up from 75 feet from the bottom, realize that if it's 75 feet from the bottom, then we only have to move it 25 feet. So our work is 4,500 times 25, which is 112,500 foot-pounds. To determine the amount of work necessary to bring the anchor and chain aboard, we first need to write an expression for the force to move the anchor and chain aboard. And once we do so, we would like to calculate that force when the anchor is halfway to ocean level and then 25 feet from ocean level. We start with our origin at the bottom, which means that the anchor is at the point 0y. Our f of y will be the weight of the anchor, which is always 4,500 pounds, plus 25 times 100 minus y, which is the amount of chain that needs to be brought onto the ship. When we do the math, we get 7,000 minus 25y. So when the anchor is halfway to ocean level, y is 50, and 7,000 minus 25 times 50 is 5,750 pounds. When the anchor is 25 feet from ocean level, y is 75, and 7,000 minus 25 times 75 is 5,125 pounds. If our origin is at the top, then the anchor is at the point 0y. And f of y will equal 4,500 plus 25 times the amount of chain that needs to be brought on board, which is 0 minus y, or negative y. And therefore we get 4,500 minus 25y. So when the anchor is halfway to ocean level, y is negative 50, and 4,500 minus 25 times negative 50 is 5,750 pounds. When the anchor is 25 feet from ocean level, then y is negative 25, and f of negative 25 is 4,500 minus 25 times negative 25, which is 5,125 pounds. The answers match. So now we want the work required to bring the anchor and chain aboard when it is first at the bottom of the ocean, and secondly 25 feet from the surface. If our origin is at the bottom, then the work is simply the integral from 0 to 100 of 7,000 minus 25y dy. We do the integration, getting 7,000y minus 25y squared over 2, evaluated from 0 to 100. And when we do the math, we get 575,000 foot-pounds. If we want to bring the anchor and chain aboard when it is 25 feet from ocean level, that means that the position of the anchor is at 0.75. And therefore we will integrate our expression from 75 to 100. And we get 120,312.5 foot-pounds. If we place the origin at the top, then we integrate our force expression, 4,500 minus 25y, but now integrated from negative 100 to 0. We get 4,500y minus 25y squared over 2, evaluated from negative 100 to 0. And again, when doing the math, we get 575,000 foot-pounds. If we want to find the force and work to bring the anchor and chain aboard from 25 feet below ocean level, we now integrate our expression from negative 25 to 0. And again, we get the same answer, 120,312.5 foot-pounds. You have to decide which way is preferable. I happen to like putting the origin at the bottom and keeping everything positive. We have seen the most common type of work problem is when we move the entire object a small part of the distance. In this case, the dx part of the integral represents the small distance that the entire object must be moved. So our formula for delta W was equal to force times the distance increment, which was f of x delta x. And therefore, our work was equal to the integral from position A to position B of f of x dx. However, there is another type of work problem where we move a part of the object the entire distance. This occurs usually when a non-rigid substance, such as a fluid, is raised or lowered. In this case, the dx part of the integral is encompassed in the force expression, and the distance is represented by a variable expression. So delta W is equal to the force increment times the distance, or delta F times x. Work is still represented as the integral from position A to position B of f of x dx. And again, this usually occurs when we pump out a liquid, as we will see in the next two examples. In number 6, we have a rectangular tank with a base 6 feet by 4 feet and a height of 4 feet, and it is filled with water. The water weighs 62.4 pounds per cubic feet. We would like to find the amount of work required to pump the water over the top edge in order to empty first the entire tank and second, just half of the tank. We use the technique that we used previously, putting the important points onto the picture. We either put the origin at the bottom or the top. If the origin is at the bottom in blue, we have the point 0, 0. The top of the tank is 0, 4, and the current water level is at the point 0y. If we put the origin at the top in red, the point 0, 0, then the bottom of the tank is 0, negative 4, and the water level will be at the point 0y. We first need to find our volume and weight of a slice of water. We look at a typical slice, and our volume will be length times width times height, which is 24 dy. And therefore the weight, or we will call the force, is equal to 62.4 times 24 dy. We next need to find the distance that the slice of water needs to be pumped to the top. This is easy. We use the coordinate at the top of the tank minus the position of the water. So if the origin is at the bottom, our distance is 4 minus y. If our origin is at the top, our distance is 0 minus y, which is negative y. We now put parts A and B together to determine the work to empty the entire tank and half the tank. If the origin is at the bottom, then our work will be the integral of the force, 62.4 times 24 dy, times the distance, 4 minus y. And we integrate that from 0 to 4. We get 1,497.6 times the expression 4y minus y squared over 2 from 0 to 4, and we end up with 11,980.8 foot-pounds. If we only want to empty half the tank, we integrate from 0 to 2. When y is 0, the distance is 4. When y is 2, the distance to pump to the top is 2. And we get 8,985.6 foot-pounds. Notice that this is very close to the total amount of work to empty the entire tank, because it takes a lot of work to pump out that water at the very bottom, because it has a long distance to travel. If we use the origin at the top, then our force is still 62.4 times 24 dy, and our distance is negative y. So the work is 62.4 integral from negative 4 to 0 of negative 24y dy. And this gives negative 1,497.6 times y squared over 2, evaluated from negative 4 to 0. Doing the math, we get exactly the same answer, 11,980.8 foot-pounds. If we only want to empty half the tank, we integrate from negative 4 to negative 2. When the y is negative 4, the distance is negative y, and we have to pump out from the bottom to the top a distance of 4. When y is negative 2, the distance is only 2. So we still get 8,985.6 foot-pounds. It is probably clear that to empty the entire tank, we use limits from 0 to 4 or limits from negative 4 to 0. But to empty half the tank, it may not be clear why the limits are what we say they are. We go into more depth on this on the next slide. We have seen the formula for draining the tank completely. If the origin was at the bottom, the work was 62.4 integral from 0 to 4 of 24 4 minus y dy. If the origin was at the top, our formula was w equals 62.4 integral from negative 4 to 0 of 24 times negative y dy. But what if we only want to drain the tank halfway? If we place our origin at the bottom, do we integrate our expression from 0 to 2 or 2 to 4? If we place our origin at the top, do we integrate from negative 4 to negative 2, or do we integrate from negative 2 to 0? In order to better understand this, let's consider filling the tank halfway. To do so, we will put in a hose connected to a water source as shown. The water obviously fills from the bottom, from y equals 0 to y equals 2, or if you want, from y equals negative 4 to y equals negative 2. No matter where we place the origin, the distance that the water travels when filling goes from 4 to 2. We put the same hose into the tank draining, but now it is attached to a pump. It is important to realize that before the pump is turned on, the water rises in the hose to the level it is in the tank. So the tank drains from y equals 2 to y equals 0, or y equals negative 2 to y equals negative 4. In either case, the distance that the water in the hose travels to the top is from 2 to 4. So while it may appear that the from the position of the hose, that the first water that is pumped out is from the bottom of the tank. It is not. The first water is from the level of the middle of the tank. The bottom line is whether we are filling the tank or draining the tank, we integrate from 0 to 2 if the origin is at the bottom, or from -4 to -2 if the origin is at the top. If we are filling the tank, we just put the water source at the top of the tank, and gravity is doing the work. When draining, the hose must be at the bottom of the tank. If not, not all the water will drain. For draining, the pump is doing the work. Number 7 reads, a conical tank has a top diameter of 10 feet and a height of 15 feet, as shown in the figure. It is filled to the top with water, weighing 62.4 pounds per cubic foot. A pump takes the water from the bottom of the tank to a level 6 feet above the top of the tank. We'd like to know how much work is done in emptying the tank. Even though the tank starts completely filled with water, let's look at it when it is not completely filled as shown in the picture. Notice that since water seeks its own level, the water in the piping will be at the level of the tank when the pump is turned off. So suppose the water in the tank is 10 feet high. That means that the water in the pipe is 10 feet high. So when the pipe kicks in, the initial amount of water needs to be raised merely 11 feet, not a full 21 feet. We start, as we did before, by labeling points. It is convenient to make the bottom of the tank the origin 0, 0. That makes the top of the tank the point 0, 15. And therefore, the top right of the tank would be the point 5, 15, because the radius is 5. And at any particular point where the water level reaches, we will label that point on the side of the tank as the point XY. To start the problem, we show a typical slice of water. We need to know its volume and thus its weight or force of that slice. Since the radius of the slice is x and its depth is dy, then its volume is pi x squared dy, and therefore its weight or force will be 62.4 pi x squared dy. Next, we need to know the distance that the slice of water needs to travel in order to get to the top of the piping. Since the slice is at the point XY, the tank is 15 feet high and the piping extends another 6 feet above it, then the distance that the slice needs to travel is simply 15 plus 6, or 21, minus y. Realize that when we set up our integral to find the amount of work done to empty the tank, there will be an x and a y in the formula. And we need to express this with one variable, so we need to relate x and y. To do this, we use similar triangles. We set up a proportion between the height and radius, y and x, of the smaller right triangle and the larger one, 15 and 5. So y over x is equal to 15 over 5, and y is equal to 3x, or x is equal to y over 3. We prefer our variables in terms of y. So finally, we are ready to write our integral to represent the work done to empty the tank. Work done will simply be an integral of force times distance. So we have W is equal to 62.4 integral from 0 to 15 of pi y over 3 squared times 21 minus y dy. We'll do all that work on the calculator to get 238,918.121 foot-pounds.